Hello, today we're continuing in our A-level physics revision series looking at atomic structure and electron energy levels. Back in 400 BC there was a debate between the Greek philosophers about what matter consisted of. Democritus took the view that if you cut something in half enough times you would eventually get to something that you couldn't cut in half anymore. It would be indivisible, the basic unit of all matter. And he called that atomos, meaning indivisible, from which we get the word atom. By contrast, Aristotle argued that there was no reason why that should be the case, and that matter should be infinitely divisible. It wasn't until 1766, over 2,000 years later, that John Dalton, a chemist, put together a number of principles which had been established by chemists at the time. He said that all elements were made of atoms, that those atoms cannot be divided, and that they combine to form compounds. At the time it was thought that atoms were indivisible, the smallest unit you could get. But as you will see from my video on the charge and mass of the electron, it was J.J. Thomson who pointed out that that wasn't right. He managed to essentially split the atom and show that it consisted of positive and negative particles. Originally, this was described as what was called the plum pudding model, or perhaps the currant bun model. Essentially, the whole of the atom was positively charged, but it had currents, or bits in it that were negatively charged. These are the kind of currants in the currant bun, or the plums in the plum pudding. The dough of the bun is the positively charged bit and is by far the massive weight of the atom. The negatively charged bits were the currants in the bun, and they were the very small weight of the atom. But Rutherford, in the very early part of the 20th century, showed that even that model wasn't quite right. He took a substance called radium bromide, which is radioactive and it emits alpha particles. And he sent them to a detector and measured how many alpha particles per minute he detected. He then put a gold foil in the path of the alpha particles. And initially he found, at least he thought he found, that there was no change in the number of particles being detected by the detector. But if he switched the detector round to here, he found that some alpha particles, not very many, were being, as it were, reflected into the detector. And this seems strange. If this model were correct, then most of the alpha particles should get caught up in the atom, in the, as it were, the positive dough. But it looks as though most alpha particles go straight through the atoms, and only a few hit anything and get rebounded. And that gave rise to a different model of the atom. Here is the atom. Here is the positive part of it in what is called the nucleus. And here is the negative part orbiting that nucleus. So then when the alpha particles come along, for the most part, they just go straight through the atom, because the atom consists of nothing. It's only if an alpha particle hits the nucleus that it will be rebounded. And since that nucleus is very, very small, only a very small number of alpha particles will be rebounded. By far the most will go straight through, out the other side, and into the detector. This nucleus we now know to be made up of positively charged protons and neutrally charged neutrons, and the negative bit going round the outside we now know to be electrons. And there are as many electrons as there are protons in a neutral atom, so that the negative charge of the electrons balances the positive charge of the protons. But there are two serious problems with this model. The first concerns the electron. Here is a negatively charged electron orbiting a positively charged proton, and a orbiting charged particle should radiate energy. And if it radiates energy, it loses energy. And if it loses energy, it must spiral in. So the electron should spiral into the nucleus and annihilate the whole atom. But clearly it doesn't, because atoms are very stable. The second problem consists of this nucleus here. If we're saying that this nucleus consists of protons and neutrons, then what we've got are several individually charged, positively charged particles called protons, all occupying a very, very small space in the nucleus. But we know that like charges repel. And so consequently, the protons in the nucleus should be pushing one another apart, and the whole nucleus should, as it were, self-destruct. So we've got two problems with this model. Firstly, the electron should spiral in and annihilate the atom. Secondly, the nucleus should self-destruct. Clearly, neither of those things happen because the atoms are very stable. So what stops these two things from destroying the atom? In this video, we're going to look at the first of these problems. Why doesn't the electron spiral in? And the key to the solution to this is to be found in my video on wave-particle duality. You'll remember that it was de Broglie who put forward the idea that an electron, which we had always thought of as a particle, might also be considered to be a wave. And he came up, as my video shows, with the idea that the wavelength of an electron is equal to h, Planck's constant, divided by the mass of the electron times the velocity of the electron. So what de Broglie was essentially saying was that you shouldn't think of an electron as simply orbiting the nucleus. Rather, if that's the nucleus, you should think of the electron orbiting, as it were, but in a wave formation. Not drawn terribly well, but essentially that is a standing wave going round the nucleus. Now, why does that make a difference? Well, it was a man called Erwin Schrödinger who said that if an electron was going to behave like a wave, then you couldn't describe it by Newton's mechanics, but rather by a wave equation. Now, Schrödinger's wave equation is quite a complicated thing. There are videos that I have made which tell you what it's all about, but you don't actually need to know it for A-level. What you do need to know is that if you take Schrödinger's wave equation and you solve it, it actually comes out with a very simple formula. It says that what's called the allowed energy of an electron that is in an atom is equal to minus R, which is called the Rydberg constant, times Z squared, where Z is the number of protons in the atom, divided by N squared, where N is any integral number from 1 to infinity. So 1, 2, 3, 4, but it can't be 1.3. The value of R is 13.6 electron volts, so it's a measure of energy. And this applies for a 1 electron atom. So you can have as many protons as you like, provided you've only got one orbiting electron. And the most obvious situation where you've got one orbiting electron is in the case of hydrogen. Now for hydrogen, you've got one proton, so Z is 1, and one electron. And so for hydrogen, E equals minus R over N squared. And that's for hydrogen. And that means that according to Schrödinger's wave equation, the electrons in an atom can only occupy those energy levels. Let's draw them out and see what they actually mean. If we draw energy along this axis, and energy is 0 here, and it's negative, we'll call this minus 13.6, for reasons you'll see in a moment. Then when n is 1, E equals minus R, and R is 13.6. So when n is 1, R is minus 13.6. What happens when n is 2? Well, when n is 2, n squared is 4, so the energy is a quarter of the value of R. So that's sort of n equals 2. When n is 3, the allowed energy level is 1/9 of the value of R. When n is 4, the allowed energy is 1/16 of the value of R. And you can see that those energy levels will continue to get thinner and thinner, or as it were, narrower and narrower, the gaps between them, until n is infinity. When n is infinity, E will be 0. And so this is, as it were, the furthest up you can go. And if you get beyond the point where the energy is 0, the electron is free. It's no longer bound to the atom. All the way down here, it has negative energy, which means it's bound inside the atom. But if it can get outside, then if it gets positive energy, it escapes from the atom's clutches. And this, of course, helps us to explain the photoelectric effect, which I showed in the video on wave-particle duality. We said that the photoelectric effect occurs when you shine light onto a metal, and provided the light has sufficient frequency, which means it has sufficient energy, you can kick an electron out of an atom. And what does that mean? Well, you might have an electron in the n equals 1 energy level, and if you want to kick it all the way out of the atom, you have to give it 13.6 electron volts of energy, and then it will escape from the atom altogether. But what happens if the photons of the light that are coming in don't have 13.6 electron volts of energy? Is anything else going to happen? Well, let's suppose we've got an electron in the n equals 1 level. Provided the photon has precisely the amount of energy between the n equals 1 and the n equals 2 level, then the photon comes in, transfers its energy to the electron, and the electron is promoted up to the n equals 2 level. Now that will only happen if the amount of energy in this photon is precisely equal to the gap in energy between the n equals 1 and the n equals 2 level. Remember, the n equals 2 is a quarter of 13.6, which means it's minus 3.4 electron volts. So that means that the incoming photon has to have an energy of 10.2 electron volts, in other words, precisely the difference between these two values. And if it does, then it transfers all its energy to the electron, and that moves it up to the n equals 2 level. You might say, well, suppose it had a little bit more energy than 10.2. Suppose it had 10.3. What happens then? The answer is nothing, because if it transfers all its energy to that electron, the electron will want to get there, which is the equivalent of 10.3 jump. But it can't go there because Schrödinger's equation says it can only occupy this energy level. And there isn't an energy level at that point. So consequently, the electron won't move. It will only get promoted if it can move to another energy level. It could be n equals 2, it could be n equals 3, it could be any value of n, but it has to have precisely the right amount of energy to enable it to do so. Now, what happens to the electron once it's got up to the n equals 2 level? Well, every particle likes to get back to its ground state of energy. So it will want to fall back to the n equals 1 because that's a lower energy level. And so shortly afterwards, and very shortly afterwards, that electron will fall back to the lower energy level. But in doing so, it will have to give off precisely this amount of energy. And it will give that energy off in the form of a photon, which we usually represent by the symbol gamma. And that energy is a precise amount. It is 10.2 electron volts. But of course, we've also shown in the video on wave-particle duality that energy is equal to Planck's constant times the frequency of the radiation. So consequently, if we know precisely what the energy is, we know precisely what the frequency of this light is that will emerge. Now you might be wondering, how can we possibly know that any of this is true when it is all happening within an atom? And the answer is that the experiment you need to do in order to show that this is true had already been done, but people didn't understand the results. If you take hydrogen in a glass tube and you pass a very strong current, make that say minus, that say plus, you get a kind of a glow inside the tube. And if you pass that through either a prism or a diffraction grating, you split it up into its constituent parts. In other words, you are looking at the spectrum of the light of hydrogen. And you find that you get 4 lines: a red line, a green line, a blue line, and a violet line. And that had already been done. Nobody knew why you got those lines, but that experiment had been done. And now we could establish why. I'm not going to draw them to scale, but let's call that n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and n equals 6. Obviously they are not equally spaced. It's more like this, but let's, for simple explanatory purposes, do it like this. What did they find? They found that the 3 to 2 jump represented the red line. The 4 to 2 jump precisely represented the green line. The 5 to 2 jump was the blue line, and the 6 to 2 jump was the violet line. In other words, the energy difference between 3 and 2 gave you an energy, and that gave you a frequency, and that frequency precisely was the frequency of this red light. Similarly for green, similarly for blue, similarly for violet. And so that very simple experiment, which had already been done, demonstrated that the reason you got these spectral lines was because of the electrons jumping between the allowed energy levels. And the fact that they couldn't jump between any other levels was the reason why there were no other spectral lines here. Now you might say, but what about electrons that jump down to level 1? Or the electrons that jump down to level 3? Why are we not seeing those there? And the answer is that, of course, electrons do indeed fall down to level 1 and 3 and 4 and 5. But anything that falls down to level 1, look at it on this one here, anything that falls to level 1 is a massive energy jump. And a high energy will be reflected as a high frequency. And a high frequency goes outside the visible range, and you go into the ultraviolet range. So anything that jumps down to n equals 1 will give off light in the ultraviolet range, and you can't see that. Similarly, any transitions at the higher level will give off a very, very small energy. And that means they'll have a very, very small frequency. And a very small frequency means that they'll be in the infrared range. So it just so happens that these transitions are the only ones that are in the light range, so we can see them. Every other transition is either in the ultraviolet or in the infrared region. It is this principle of getting electrons up the energy level and back down again which is at the heart of a laser. A laser stands for light amplification by stimulated emission of radiation. What happens is that you take a substance and you may have an electron in the ground state. You might heat it or put an electric current through it in order to give energy to the electron and promote it to a higher level. Now, whilst it's at a higher level, if a photon comes in and hits it, then what will happen is the electron will be driven back down to its lower state, but the original photon will continue with another photon which will come out as a result of this transition downwards that just happens to be of exactly the same frequency and exactly the same phase. So because you had an electron in an elevated state and you bring in a photon of a certain energy, you can push the electron back down to its ground state and produce another photon with exactly the same frequency and phase as the original one. So whereas you had one photon, you now have two. So let's have a look at a crystal that you might use in the middle of a laser. And you've got this principle happening. Photons of light are producing two photons of light. And the light, of course, will be escaping in all directions. We're not worried about that. But let's suppose we put two mirrors at either end. Now we'll have photons that are being produced and sent to the mirror, and then they come back again. But when they come back, they hit an elevated electron, knock it down and produce two photons. So now two photons hit the mirror. They are now reflected. They in turn will produce four photons which hit the mirror. They will be reflected. And every time they pass through the crystal, probably more than once, they will produce twice as many photons as there were before. That's light amplification. And what you get effectively is a constant beam between the mirrors, which is amplifying all the time and getting more and more intense as more and more photons are generated. If you have a small hole in the mirror there, then some of those photons can emerge, and that is the laser light. The way it actually works is that you have a ground state, you have an unstable state, and you have a metastable state. And what happens is you use perhaps electricity to push the electron up to the unstable state. It will then fall to what's called the metastable state, and it's whilst it's in that state that a photon comes in, hits it, causes the electron to fall down to the ground state, and generates another photon, so that you now have a pair of photons that are exactly in phase and exactly the same frequency. And that goes on backwards and forwards between the mirrors to produce a very coherent, very intense source of light that is all in phase, and that's called laser light. Matter should be infinitely divisible. It wasn't until 1766, over 2,000 years later, that John Dalton, a chemist, put together a number of principles which had been established by chemists at the time. He said that all elements were made of atoms, that those atoms cannot be divided, and that they combine to form compounds. At the time, it was thought that atoms were indivisible, the smallest unit you could get. But as you will see from my video on the charge and mass of the electron, it was J.J. Thomson who pointed out that that wasn't right. He managed to essentially split the atom and show that it consisted of positive and negative particles. Originally, this was described as what was called the plum pudding model, or perhaps the current bun model. Essentially, the whole of the atom was positively charged, but it had currents, or bits in it that were negatively charged. These are the kind of currents in the current bun, or the plums in the plum pudding. The dough of the bun is the positively charged bit and is by far the massive weight of the atom. The negatively charged bits were the current, that there was no change in the number of particles being detected by the detector. But if he switched the detector round to here, he found that some alpha particles, not very many, were being, as it were, reflected into the detector. And this seems strange. If this model were correct, then most of the alpha particles should get caught up in the atom, in the, as it were, the positive dough. But it looks as though most alpha particles go straight through the atoms, and only a few hit anything and get rebounded. And that gave rise to a different... Hello, today we're continuing in our A-level physics revision series looking at atomic structure and electron energy levels. Back in 400 BC, there was a debate between the Greek philosophers about what matter consisted of. Democritus took the view that if you cut something in half enough times, you would eventually get to something that you couldn't cut in half anymore. It would be indivisible. the basic unit of all matter, and he called that atomos, meaning indivisible, from which we get the word atom. By contrast, Aristotle argued that there was no reason why that should be the case, and that months in the bun, and they were the very small weight of the atom. But Rutherford, in the very early part of the 20th century, showed that even that model wasn't quite right. He took a substance called radium bromide, which is radioactive, and it emits alpha particles. And he sent them to a detector and measured how many alpha particles per minute he detected. He then put a gold foil in the path of the alpha particles. And initially he found, at least he thought he found,